This is a tutorial on finding patterns in mathematics. If we were traveling down the highway at a speed of 50 miles per hour, and every hour we wrote down the total distance that we had traveled, well then after the first hour we would find that we had driven 50 miles. After the second hour we drove 100 miles. After the third, 150. After the fourth hour we'd find that we had driven 200 miles. After the fifth hour we would have driven 250 miles. Now if we look at these distance numbers, 50, 100, 150, 200, 250, there is a pattern between them. To go from 50 to 100, we're adding 50. To go from 100 to 150, we're adding 50. Between 150 and 200, that's a jump of 50. And between 200 and 250, that's also a jump of 50. Because these numbers have a pattern between them, and they're listed in order, we would call these numbers a sequence. Now when we have a sequence, we call every term in that sequence A. And then with that A, we usually have a subscript that tells us the place in the sequence that term belongs. So A1 would be the first term in our sequence. And in that case, our first term, that would be 50. Our second term in this sequence is 100. The third term, or A3, would be 150. A4 would be 200, and the fifth term, A5, would be 250. If we had a sixth term, or we wanted to find A6, well, we would just follow the previous pattern of our sequence. We go up 50 every time we find a new term. So if we're at A5, or our fifth term, and that's 250, and we add 50 to that, we should find that the sixth term, if we drove for 6 hours, would be 300. Now frequently when you deal with sequences, you'll see the terminology a to the n. A to the n is the term in this sequence, but we don't know which term in that sequence. N is the position of that term. So if n was 3, then a to the n would be equal to a to the 3. If we had the sequence 3, 9, 27, 81, and 243, well then the third term, or a3, that would be 27. If our n position was 4, that would mean that 4 would be n, which means a to the n would be a4, and in this sequence, a4 is 81. So if I said that I was looking for a to the n when n was 5, that means that a to the n is a5. And in this sequence, a5 is 243. Other common notation that you'll find other than a to the n is a to the n minus 1 or a to the n minus 2. A to the n minus 1 just means that we're subtracting 1 from n. Well again, a to the n is some term in our sequence. So if we have a to the n minus 1, then that just means that n is 1 less, or this is the term before a to the n in the sequence. A to the n minus 2 would be the term 2 terms before a to the n in the sequence. So for example, if we said that n was equal to 3, that means that a to the n would be a3. If n is equal to 3, that means a to the n minus 1 would be a2. A to the n minus 2 would be a1. Well, in this sequence, 3, 9, 27, 81, a3 is 27. So that means a to the n minus 1 would be 9. And a to the n minus 2, well, that's just 3. Now, if a to the n was a different term in our sequence, say n was equal to 4, that means that a to the n then would be 81. a to the n minus 1 is the term before that one, so that would be 27. And a to the n minus 2 is the term before that term, so a n minus 2, that would be 9. All this notation is important because frequently we try to make formulas that describe our sequences. So again, if I have the sequence 3, 9, 27, 81, and 243, well, the pattern here is that each term is multiplied by 3 to get the next term. To get 3 to 9, I multiply by 3. To go from 9 to 27, I multiply by 3. From 27 to 81, again, I multiply by 3, and 81 to 243, I multiply by 3. Now, if 3 is A1, 9 would be A2, 27 would be A3, and so on. That means that I found A2 by taking A1 and multiplying it by 3. I also found A3 by taking A2 and multiplying it by 3. In fact, every term, A4, I get by taking A3 and multiplying it by 3. If I wanted to write a generic equation for every term in this sequence, I would say that a to the n, depending on whatever term n is, that's always equal to 3 times a to the n minus 1. A2 is a to the n. A1 is the term before A2, or a to the n minus 1. So this could be a formula that describes this sequence of numbers. Now there are two different general types of formulas that we can write that describe sequences. The type that we just found, or we just developed, was a recursive formula. Another type of formula that describes a sequence would be an explicit formula. A recursive formula is a formula where a sequence is dependent on the previous term. So each term is dependent on the term before it. For example, a to the n is equal to 2 times a to the n minus 1. Every term in our sequence is equal to 2 times the term before it. So if we ever write a formula that describes a sequence that has previous terms in the formula, then this is a recursive formula. Now, an explicit formula is a little bit different. An explicit formula tells us that each term in our sequence is found by using the number of terms. Think of that as n. So if I have a to the n, the nth term in my sequence, that's equal to 2 to the n minus 1 power. Notice that this isn't an a to the n minus 1 term. This is 2 to the n minus 1 power. N is the power, not a to the n, or a to the n minus 1. This is an exponent, not a subscript. So if you ever see n in the formula, then you're writing an explicit formula. So now let's take some time and practice our ability to identify explicit or recursive formulas. In our first example here, we have an is equal to 2 times an minus 1 plus 3 times an minus 2. This means that every term in our sequence, an, is equal to 2 times the term before it, an minus 1, plus 3 times the term before that, an minus 2. Because this formula includes previous terms in the sequence, that makes this a recursive formula. So look at our next example. Here we have an is equal to 1 plus 2 to the n power. This n power is not a subscript, this is an exponent, which means every term in our sequence is equal to 1 plus 2 times the position of that term. So since this formula includes the position, or n, that makes this an explicit formula. Our next example is an is equal to 13n minus n squared. So every term in our sequence is equal to 13 times the position of that term minus the position of that term squared. So again, because we're including the position, or n, in our formula, this becomes an explicit formula as well. Our last example, an is equal to 4 times an minus 1 plus 5. This means that every term in our sequence is 4 times the term before it plus 5. Since our formula includes previous terms in our sequence, that makes this a recursive formula. So now let's try writing a recursive formula for this sequence. Here we have 50, 47, 44, 41, 38, and 35. So we want to write a formula, and then we're going to use that formula to find our 7th term and our 10th term. Well, to go from 50 to 47, we subtract 3. To go from 47 to 44, we subtract 3. From 44 to 41, we subtract 3. From 41 to 38, we subtract 3. And from 38 to 35, we subtract 3. So we can see our pattern here. Now this is A1 because it's the first term in our sequence. This one would be A2 because this is the second term in our sequence. A3, A4, A5, and A6. Now we're writing a recursive formula, so that means that our formula is going to include previous terms. Well, let's look at A2. A2 is equal to A1 minus 3. Okay, well, let's look at A3. A3 is equal to A2 minus 3. And A4, that's equal to A3 minus 3. So every term in our sequence, say a to the n, or an, that's equal to the previous term. So we would say an minus 1 minus 3. So this is our recursive formula for this sequence. Next, we want to find our 7th term. Well, okay, we're looking for A7. And that means that that's going to be equal to the term before it, so A6 minus 3. Do we know A6? Well, we do. It's 35. So A7 is going to be equal to 35 minus 3. So A7 then is equal to 32. Now let's find A10. Well, okay, A10, that's equal to the previous term, so A9 minus 3. Except I don't know A9. But I can find A9. A9 is equal to the previous term, so A8 minus 3. Well, except I don't know A8 either. So A8 is equal to A7 minus 3. Well, I do know A7. I just found it. That's 32. So if I plug that in, that means A8 is equal to 32 minus 3. So A8 is equal to 29. And if I plug that back in here, I'll find out that A9 is equal to A8. So 29, and then minus 3. So A9 is equal to 26. And that means that A10 is equal to 26 minus 3 because it's A9 minus 3. So A10 is equal to 23. So we found A10, but imagine if we had to find A50. That would be very hard using a recursive formula. So instead, let's talk about explicit formulas. So let's try writing an explicit formula for the sequence 3, 6, 9, 12, and 15. Then let's try to find our 7th term, our 10th term, and our 26th term. Now remember, an explicit formula includes the position, so it's going to have n in it. We have a sequence that's 3, 6, 9, 12, and 15. And to go from 3 to 6, we add 3. And from 6 to 9, we add 3. From 9 to 12, we're going to add 3. And from 12 to 15, we add 3. So we can see the pattern between these numbers. In this case, A2, that's equal to A1, our first term, plus 3. A3, well, that's equal to our second term, which is A2 plus 3. And so on and so forth. If we wanted to find A4, that's equal to A3 plus 3. But these aren't helping us find an explicit formula because none of these formulas have n in them. Well, let's look at this value of A2. This is A1 plus 3. Let's say I took this and I plugged it in for A2. I would find out that A3 is equal to A1 plus 3 and then plus 3 again. If I took this value for A3 and I plugged it in here for A4, I'd find out that A4 is equal to A1 plus 3 and plus 3. We could keep doing this. This is A5. That's equal to A1 plus 3 plus 3 plus 3 and plus 3. So when I was looking for A2, I added 3 one time. When I was looking for A3, I added 3 two times. A4, I end up adding 3 to A1 3 times. When I was looking for A5, I took my first term and I added 3 4 times. This number of times that we're adding 3 is going to give us our n value. Our explicit formula is a to the n is going to be equal to, now A1 is what's common in all of these formulas. So a to the n is going to be equal to A1. But then we're going to add 3, but we're going to add 3 a certain amount of times. We're going to add it n minus 1 amount of times. So if I'm looking for the third term, I would start with my first term, and I would add 3 times n, which in this case is 3, minus 1 times it. So this is A3 is equal to our first term, which is 3, plus 3 times 3 minus 1, so 2. So A3 would be equal to 3 plus 3 times 2, or 6. 3 plus 6 is 9. And A3 is indeed 9. So this is the formula, or our explicit formula, for this sequence. Now if we want to find 7, or the 7th term, we just plug in 7 in for n, and our first term, which is 3, in for A1. So A7 is equal to 3, which is our first term, plus 3 times n, which is 7, minus 1. So A7 would be equal to 3 plus 3 times 6. 3 times 6 is 18. Add 3 and you'll find that A7 is equal to 21. If we want to find A10, or our 10th term, well, A10 is equal to our first term, which is 3, plus 3 times 10, the position of our term, minus 1. So A10 is equal to 3 plus 3 times 9. 3 times 9 is 27. Add 3. That means our 10th term is equal to 30. Lastly, we want to find our 26th term. So we find A26 is equal to our first term, which again is 3, plus 3 times 26 minus 1, n minus 1. So our 26th term is equal to 3 plus 3 times 25. 3 times 25 is 75. Add 3 and we'll find out that our 26th term is 78. So that is how you write and use explicit formulas for a sequence. And that completes the tutorial on finding patterns in mathematics.